Hello, everybody. Welcome to OpenCV weekly webinar. And today we have a very exciting presentation. And we have with us Professor Pranav Rajpurkar from Harvard University and Mark Endo from Stanford University, who are going to present a very exciting field of study, which is image segmentation with medical image segmentation with semi-supervised learning. So let me first start by asking Professor Pranav to introduce himself. Pranav.
Hey, hi. Thanks for having me here, Satya and Phil. So I'm Pranav. I'm an assistant professor of biomedical informatics. I've spent the last few years working on AI and medical image interpretation. So I think about how we can get deep learning to read images at the level of experts. And once we have developed those, how do we bring those back into clinical settings where we can use these tools to help physicians make their decisions?
That's great. Mark?
Hi, yeah, I'm Mark Endo. I am a BS candidate at Stanford University studying computer science, and I do research with Pranav on medical image model interpretability, as well as some work on radiology report generation methods. Great to be here.
That's great. And just to give a background, Professor Rajpurkar's group was the first group that beat a radiologist level, that received radiologist level accuracy in pneumonia detection. So that was a huge breakthrough. And it opened up our eyes that you can actually beat radiologists in some of these tasks. So it was an illuminating paper, to be sure. Also with us is our own Phil Nelson, who is the content manager at OpenCV.org. He's responsible for putting together this webinar, as well as OpenCV competitions, etc. Welcome, Phil.
Yeah, good morning out there, folks. It is I, once again, the co-host with the co-most, the second banana who is second to none, the next best thing, Phil Nelson. Here on OpenCV Weekly Webinar, we do a couple of things every week, one of which is a special trivia giveaway to one of you lucky Zoom viewers in the audience. Later in the webinar, we will ask a question based on the slides from the presentation here, and the first person to answer that correctly will win a copy of TensorFlow, Deep Learning with TensorFlow and Keras from the ongoing Kickstarter campaign of OpenCV. We'll drop the link in chat for that as well. We'll also be doing Q&A from you live in the audience, so please use the little Zoom Q&A button at the bottom of the screen to ask your question at any time, and we'll do our best to work it in here.
All right, and we have a slight change in format this week because Professor Rajpurkar has to leave after 30 minutes. We will actually start with Professor Rajpurkar. He'll answer any questions you may have about image data or image analysis or segmentation, detection, whatever in medical image processing in the beginning of the show. And then, we will move on to the actual presentation about image segmentation. Okay.
Sounds good. We've already got one question about Pranav's bike.
All right, Pranav, it's your show now.
Great. Well, excited to share our work with you today. And we're going to spend a lot of time talking about semi-supervised learning and how that applies to medical image segmentation. And Mark and I will chat about that over the next many minutes. But I thought I'd start out by sharing a little bit about the space of AI in medicine and why it's a really exciting time for this space in terms of all the progress that's happened. Let me share a few examples. So first, we have now hundreds of FDA-cleared technologies, a lot of them using deep learning to look at many different fields where image interpretation is important. We have algorithms that can look at chest X-ray images and diagnose different conditions. We have algorithms that can look at electrocardiograms and be able to detect abnormal heart rhythms. If we look at the kind of evidence that's being generated in the field in terms of research, there's several randomized control trials now that are demonstrating that these technologies can improve patient outcomes and physicians' lives. As examples, there are tools that can, during a colonoscopy, detect polyps, and these polyps may turn into cancer. Before they do, when these are detected, they can be removed by the gastroenterologist. That's an example of how we're already demonstrating that we can improve lives using AI. Finally, an important part of the puzzle is how do we figure out how companies can make money from these technologies in a way that allows them to grow and scale such that these technologies can be widely applied. And two breakthroughs that have taken place over the past few years is that there are now CMS coverage of AI algorithms. So this is where insurance is able to reimburse every time an algorithm is used for detecting something, such as for retinal fundus images, detecting diabetic retinopathy, or looking at images of the head when a patient is admitted into the emergency department and check for signs of stroke. These are some of the ways in which medical AI has advanced in the past few years. I thought I'd share a little bit about what does the future of this space in terms of algorithms. A lot of you in the audience are probably interested in how these are built. What does the future look like? And one challenge right now that the field is facing is that the way we're developing these algorithms is going to be difficult and expensive to scale labeling for every task. And some of the solutions that have emerged in the past few years that have worked out really well is one, transfer learning and self-supervised learning. I just want to share what these concepts are at a high level today. Well, let's start with transfer learning. The idea behind transfer learning is I'm going to learn a convolutional neural network, which is a type of neural network that's especially well suited to image data. And I'm going to first learn a network to identify from images of the world, what is the object in that image. So here I have an image of a penguin, and I can learn to distinguish that this is a penguin, this is not a cat, this is not a dog. And this knowledge that this network learns is then a good starting point for a medical task. In the medical task, now we don't have a natural image of the world around us. What we have is a very specific image here of a patient's chest, and this is a chest X-ray. And from this, we want to now identify whether there is a mass or no mass, whether there's pneumonia for the patient, whether the patient has edema or several other conditions. The idea of transfer learning is to say I'm going to have a pre-training step that's going to allow me to learn some knowledge that's going to be useful for me in the so-called fine-tuning stage. And transfer learnings work really well for many years. I want to share another emerging paradigm recently. The idea behind self-supervised learning is that I don't need labels of the world around me to serve as a starting point. What I'm instead going to do is I'm going to use unlabeled data to come up with a signal from the data that's going to serve as my learning task. And that's what we call the pretext task. And then we're going to use that as a starting point on labeled data. And here our labeled data might label chest X-ray images for different diseases. And that's the self-supervised learning paradigm. We can apply it to chest X-rays, and we did this last year. And then we're able to show that when we have only a fraction of the labeled data, we're able to do much better. So what is the implication of this? The implication is that we don't need that much manual annotation to collect labels to ask radiologists, hey, what's in this chest X-ray image, to do just as well, because we're able to leverage unlabeled data using self-supervised learning. So let me talk.
Could you explain a little bit in the context of chest X-rays, what is this self-supervised task? With unlabeled data, what do you achieve? And then how do you use labeled data to do the knowledge transfer?
Yeah, so with chest X-ray images, the basic idea in which self-supervised learning applies is as follows. You take, let's say, my chest X-ray image. So I'm going to have that image, and then I'm going to have maybe another chest X-ray image of me. So we have those two images. We're going to tell the network those two belong to the same patient. I'm going to say those two have information, and I want you to encode that those two are similar to each other. While let's say we got your chest X-ray, we would then encode that your chest X-ray is different from my chest X-ray. Now here, we didn't use any labels. We didn't ask a radiologist to interpret them. We just said, this is what similarity looks like. This is what this dissimilarity looks like. So that becomes the pretext task. Then in the supervised target task, I take that network, which has learned this, and I say, okay, now I'm going to collect labels, whether there's edema, whether there's consolidation, and so on. And that's the fine-tuning step here.
Thanks.
Great. So I want to talk about medical data annotation because that's a very important piece of the puzzle. And I want to share one way in which we can get creative with medical data annotation. I'm going to use as example the release of the NIH chest X-ray 14 dataset, which is about 100,000 examples that were made available to the public in 2017. And the way this data set was annotated is as follows. When radiologists interpret an image in a clinical setting, they often dictate a radiology report. This radiology report is used by a physician to then make a recommendation on what the next step for this patient is in terms of their care. But the idea that this team used is it said, I'm going to annotate a chest X-ray based on the associated report that was dictated by the radiologist at time of interpretation. And so here we can build a report labeling natural language processing system, which says, is this disease present, is this absent, or is this uncertain? And then you can label the image accordingly, using 1 if it's present, or 0 if it's absent or uncertain. And this can work well, but the challenge is this is difficult to get to work well. When this data set was released, a lot of radiologists recognized that there was a lot of errors in this data set. But this is out of a random sample. One radiologist highlighted in their blog post the images on which they disagreed with the label. And so this is a high amount of label noise and might be difficult to build good models with this high level of label noise. So we looked at, can we improve this method of generating labels from these reports? And this was one of the problems we took on in 2018, where we said, we're going to think about this problem in 2 steps. One step is going to be, I'm going to recognize what are all the mentions of different diseases in the report, and those are annotated in red. And after I do that, I also want to associate with those mentions whether there are attributes such as whether there's uncertainty or negations. So for example, in the first case, you see cardiomediastinal silhouette, and then that's modified by this term unremarkable, which means that that is normal. And so we go into the corresponding structured output here, and we say for enlarged cardiomediastinum, which corresponds to this mention, I'm going to associate it with a labeler output of 0. So then how do I automate this process? Well, we can use natural language processing techniques. And here we can see that we improved over the previous best labeler for going from these reports to the structured outputs. And we used this technique to then label a large data set that was being released from BI, and that's local here, with a group at MIT and at Harvard. And we showed that even on their data set, we were able to extract labels with high accuracy. We made the data set that we released from Stanford available to the public. That's called the CheXseg data set, which contained about 200,000 examples. And we had a corresponding competition associated with this data set, which allowed anyone in the world to be able to develop image classification models on this data set. And we've done similar releases with other competitions, including MURA and MRNet, which look at detecting abnormalities in bone X-rays or knee MRIs. Shortly, Mark is going to spend some time talking about what we learned from the CheXseg data set and how that enables us to do medical image segmentation in addition to classification. But before that, I just want to maybe wrap up here by sharing a little bit about what is exciting me right now and some of the directions my lab is taking. Broadly, our mission is to build and translate medical AI into the clinic. We think about how do we go from label intensive to label efficient medical AI algorithms? How do we enable a world in which clinicians and AI are collaborating together to improve patient outcomes? And how do we build data sets which allow people to solve these very important and interesting problems and advance our knowledge in the community? Broadly, we work on imaging and sensors. There's several people in my lab that are either AI experts or medicine experts, and we work broadly with global partners in industry and on the hospital side. Here's some references in case you want to learn more. I'll just end with some opportunities to learn more about the space. And if you're interested in learning about some of these techniques, we have an AI for Medicine 3-course series on Coursera, which I have instructed. I'm a co-host of the AI Health podcast, where we talk to a lot of entrepreneurs, investors, and scientists about what's going on in the space. And I am also co-editor of a weekly newsletter called the Dr. Penguin newsletter, which highlights latest developments in the AI health space. For those at Harvard and Stanford, we currently have a program for closely mentored research at the intersection of AI and medicine. I'll end there, maybe take a few questions if we have the time right now, and then I'd love for us to share, and Mark will share this, a deep dive into one of our very exciting projects on combining expert annotations with saliency maps for chest X-ray segmentation.
That's great. Thank you so much. And I also want to, for people who are more technical, who are at a level where they can read papers, I also recommend Dr. Rajpurkar's group has a YouTube channel where they discuss weekly, I think, a paper in medical image, medical images, or just general computer vision techniques as well. So that could be very useful as well for people who are a little bit more advanced, because that's discussing a paper. You need to be able to read papers, and you should be at that level. Yeah. So questions for...
Yeah, we've got one early question here from Thanos. Would like to know what kind of data is required for training here? Like how much is the question?
Sure, that's a great question. And my 2022 answer is think about the input data and the labels differently. So the current trend is unlabeled data, having a lot of it is very helpful. For labeling, for labeled data, you could get away with a small fraction of that being labeled. This is a particularly strong area of interest for my group, is how do you enable development to happen if you have access to a large unlabeled data set, but very small number of labels.
Yeah, I mean, that makes sense. Now I'm interested to know what the 2021 answer would be.
Well, I think my answer, and maybe not a 2021 answer, but I think really self-supervised learning over the last few years has made this transition into thinking about large unlabeled data sets, very, very meaningful at this point.
Yeah, and as Dr. Jan Lacan says that, reinforcement learning is the cherry on the top of a cake. supervised learning is the icing on the cake, but the bulk, the actual thing is self-supervised learning. So that's definitely very interesting.
We're going to end up making our first T-shirt with a cake on it, aren't we? I've got a question, which is so you mentioned some other data sets and stuff here, as well as the competition. What sort of how do you choose which of these things to work on? It seems like you could go in essentially any direction with this sort of image annotation and machine learning in medicine, because it's still such a new addition to the field. How do you decide what to do next?
Yeah, so maybe let me make let me share this from a couple of different perspectives. So two of the modalities we work most with is X-rays and ECGs. X-rays are the most common diagnostic image procedure in the world. This was a striking statistic, but there are 2 billion chest X-rays that are taken per year. 2 billion.
Wow.
In terms of ECGs, I just have the stat in US alone in 1 year, there's 200 million ECGs. So that's the scale that we're talking about. So if we're thinking about problems that apply to a lot of people daily, these are the places to start. There are a lot of interesting challenges about what machine learning problems to formulate from these modalities. And I think a lot of that is driven by what we observe as being challenges in the field for the folks that are translating these technologies, and for the folks that are trying to make sure that these are going to be effective. And so part of our role as academics is to enable progress on really challenging technical issues around the development of these, but also set up ways of frameworks of understanding the risks of having these deployed, and asking questions about how well these models generalize. And that's the role that we're trying to fill.
Yeah, thanks for the detailed answer. Johnny would like to know, what scores do you consider production ready for this sort of sensitive use case where it very much matters if it's good enough?
Yeah, that's a good question. And in getting approval with a lot of regulatory bodies, you often have to pre-specify what you expect to be the sensitivity and specificity endpoints, which basically says, I want to make sure this is how well my algorithm works even before I test it. And the way that's often done is by some sort of a measurement of how well do people do in practice today. Because right now, if we know that this is the general performance of someone who is trained with these many number of years of experience, then that could be a benchmark.
So for FDA approval, do they expect you to beat human level accuracy or radiologist level accuracy? Or these are assistive technologies, so the bar is lower. You could say that this is just assisting the radiologist, so you don't actually need to beat the radiologists. Could you?
You can specify your intended use and your endpoints, and these can be in conversation with folks at the FDA. But there has been a diversity in terms of intended uses and in terms of the endpoints that have been set up, because they are task specific.
Right.
A couple folks have asked, I know you have to bounce here relatively shortly. A couple people have asked, what's the best way to get in touch with you if they have questions or would like to sit under the learning tree, as it were?
Sure. So on my website, there is an email, and that would be the best way to reach me. And if you want to keep in touch with what's going on in the lab, then there's also a mailing list you can sign up to on the lab webpage, or follow us on our YouTube channel.
And the main site to find you would be your GitHub. That's the one I found.
Yeah, that's right.
Okay, I'll drop that link in the chat.
Great, thank you.
Thank you so much for coming here and engaging the audience with this new field. I mean, for a lot of people, medical image is pretty new, and thanks for doing that. I also wanted to point out that I keep saying in this webinar that great careers will be made when you work at the intersection of two different fields, like you're working at the intersection of medical imaging and computer vision. And that's such a sweet spot for a great career. And I wish you all the best from the entire community.
Yeah, thank you. Thank you very much. Thanks for having me. And I hope you enjoy the second part of this talk on where we are diving into a very specific, exciting research question.
Thanks.
Yeah, and we'll be doing more questions during the show here, folks. Pranav just has to roll to a previous engagement, but Mark here will be continuing on with the presentation, and we will still be doing our trivia giveaway in about 20 minutes or so. So stay tuned for that.
Thanks, Pranav. Bye.
All right, Mark.
All right, Mark, I'm
yours.
very excited about your presentation specifically because it does relate to something that I'm working on right now. So please, I'm all ears.
Okay, great. Yeah, thank you. So hello, everyone. I am super excited to be presenting a deep dive into a work that we worked on last year, which was called CheXseg, combining expert annotations with DNN-generated saliency maps for X-ray segmentation. All right, so as Pranav was mentioning, for the prediction of pathologies from chest X-rays, so all of these labeled predictions, models have reached already a very high accuracy, even beating radiologists in some settings. So here we're looking at the CheXpert competition leaderboard, where we see that the top methods are performing better than radiologists. And this is noted with the metric number of rads below the curve, which is basically the number of radiologists below some metric curve, such as the area under the ROC curve. So we're finding that these models are performing very well on this task. But one downside is that these models are often lacking interpretability. So they will take an chest X-ray image as input, they'll have some intermediate steps, and then they will output pathology probabilities at a very high accuracy. But one issue is that the reason why they're making the predictions that they do is often unclear. So this sort of black box nature of neural networks represents a barrier to physicians' trust and model adoption in the clinical setting. So one potential solution to this is the introduction of saliency maps. So saliency maps are a popular set of explanation methods that highlight regions of the image that are most important for the disease classification. So as we can see on the image here, there are highlighted regions on the X-rays in this orangish purple color, and they represent the portions of the images that ended up being most influential in the model's prediction. So in this case, these regions were the ones that ended up leading most of the predictions of airspace opacity, pleural effusion, and support devices. Now,
support devices, what is support devices? What is support devices actually?
Yeah, so in this case, support devices isn't technically a pathology, but we just kind of group it in because it is one of the labels that is used for the CheXpert competition. But it's basically any device that's implanted to help support.
Like a pacemaker or something like that.
Yeah, like a pacemaker would be an example.
Would that also include like, metal chunks of metal on your collarbone or whatever to keep it in place, that sort of thing?
Yeah, so the exact specifications of what counts as a support device is also sometimes a little bit unclear. I think I could be wrong, but I think generally like just a metal plate wouldn't count as a support device. It would have to be some sort of some sort of device that serves more of a purpose than just like
Something more
keeping two bones
mechanical.
together.
Sure.
Yeah.
Gotcha.
Yeah. All right. So moving on, although these saliency maps show some sort of interpretability from chest X-rays, they have been shown to be untrustworthy for medical image interpretation. So sort of in general, the saliency map segmentations, they fail to capture the geometric nuances of given pathologies. And instead, they will produce some coarse, low resolution heat maps. Looking more specifically, here we see that the gap in localization performance between the saliency maps and humans is largest for pathologies that have multiple instances or are smaller in size or have shapes that are more complex. So with the image here on the top left, we can see that the edema has multiple instances as shown with the blue ground truth segmentations, but then the saliency method output in purple ends up being just one blob that sort of covers one side, and it's not really capturing the anatomy well here. And also looking at the top middle with the size, so airspace opacity here is a pretty small location, but the saliency map is kind of overshooting and just sort of getting this general area of where the airspace opacity is. Again, not really following the anatomy. And there's also an artifact here on the top right of the chest X-ray image, which we wouldn't want. And then on the top left, we're looking at a pleural effusion here, which is a pretty complex shape in this excess fluid here around the lung. And we see that the saliency map is not capturing any of the complexity here, which is definitely an issue. So looking at the geometric features below, just something to note that in this particular task, you could have multiple number of instances, varying sizes, elongations, and irregularity differences. So we have a cardiomegaly that is just one instance versus a atelectasis shown here could be two instances, and then it's going to be harder for these saliency maps to get the two instances right compared to just one instance. Looking at size, generally something that's bigger in size is going to be easier to correctly segment. So enlarged cardiomediastinum here is quite large, whereas the lung lesion here is, this nodule is quite small. And then elongation, so saliency maps are generally going to have an easier time with things that have low elongation, such as this airspace opacity, versus a support device, as you can see here, which is quite elongated. And then lastly, irregularity. Saliency maps are going to have a harder time with things that are highly irregular. So with these issues in mind, looking at these aspects more quantitatively, we see that saliency maps are performing significantly worse compared with humans. So on the left side here, these are all the pathologies where the saliency map methods are underperforming humans. In the middle, we see statistically insignificant pathologies where the saliency methods in humans perform about the same. And then on the right, we're seeing where saliency methods are actually able to outperform the human benchmark.
Quick question. So what you're saying is that for a lot of problems, even though the actual network has outperformed radiologists, when you actually try to go and look at the saliency maps, recover the saliency maps using one of the techniques, we see that the saliency maps are not outperforming the humans, right? Ideally, we want that, oh, not only tell me what the pathology is, but you also tell me where it is located so that I can check for myself. Is that the right interpretation of this?
Yes, exactly. So these models that are performing classification are doing very well, but in order for these to be adopted in the clinical setting, ideally, a radiologist could look at the output and ask why it is that it made the prediction that it did.
Right.
And to do this, typically you would use some sort of saliency maps that give you insight into why the model made the prediction it did, but we're finding that it's not actually making the prediction off of just the area of the pathology that is of interest. Sometimes it could use some confounding factors or something else in order to make its prediction.
Right. Okay.
And then from here, so one solution that you could have to kind of eliminate this inaccurate saliency map issue is that you could train some segmentation model that can produce more accurate pixel level maps. So in this case, the model would not just be predicting the overall labels of 0 and 1s for each class, but it would be going through the whole image and per pixel deciding if each pixel belongs to the certain classes. So this becomes a much more complex task in that way. And the issue with this task right now is that the training is typically limited by the time-consuming process of collecting expert annotations that you can train on. So like
and that radiologist in the loop is very, very expensive.
Yes, it's also quite costly. To have radiologists go in some program and annotate every pixel of a chest X-ray image on what pathology it might be indicative of. So one question here is, what would happen if you were able to combine the scale of the coarse DNN-generated saliency maps that we looked at before with the high quality of the pixel level expert annotations for training a multi-label semantic segmentation model? So that is the question that we go after with this research of, can the combination of saliency maps and expert annotations for training medical image segmentation models provide higher quality segmentations at a lower cost?
Right. So that is the semi-supervised part of it. Saliency maps are free and expert annotation is the supervised part.
Yeah, exactly. So in this case, we're using semi-supervised to mean that the sort of strongly supervised part or fully supervised part is those expert annotations. And then the weakly supervised part is just using the classification labels in order to produce these saliency maps.
Got it.
So yeah, even like the sort of weakly supervised part is using some sort of label, and the fact that it needs these classification labels for the saliency map outputs.
Okay, sounds good.
So in terms of setup of the problem, so here the task is to classify each pixel of a chest X-ray image into 0 or more of 10 possible pathologies. And the data set that we use here is CheXpert, where there is around 220,000 chest X-ray images of around 65,000 patients. And the validation set here for the semantic segmentation model is 200 radiologist annotated chest X-rays with a test set of 500 radiologist annotated chest X-rays. So one thing to note here is that validation set of 200 chest X-rays is all of the expert labels that we have access to besides those 500 chest X-rays used for the test set. So in order to actually implement our method, we're going to have to use a subset of that to train our data on and then validate on the rest of it. So for our particular setup, we used 150 of those radiologist annotated labels as a train set. And then that meant that we could save 50 of those examples to use as a validation set. And we ended up selecting this validation set of 50 labels or 50 annotations to exclude scarce pathologies, as we found that examples of those pathologies were actually most valuable in the training process. But this also meant that when we were evaluating the performance on this validation set, we only looked at the performance on the most common pathologies. So there might be some introduction of bias here with just such a small validation set and kind of maneuvering around the obstacles of such a small validation set. But we found that it ended up resulting in the best possible findings that we could based off of what access we had. So in terms of evaluation metrics, we use the MIOU score, which is the mean intersection over union. So basically, it's the area of overlap between the predicted segmentation and the ground truth segmentation over the area of union between the two, the ground truth and the predicted segmentation. So we take this IOU scores for every pathology, and then we average them across all the pathologies to create this MIOU score. And below here, we're just looking at some sort of canonical examples of what a poor, good, and excellent MIU score, or in this case, it's IOU score. So our model that we proposed here is CheXseg, which is a semi-supervised method for multi-pathology segmentation, where there's two steps. The first one is per pixel segmentation masks being created by processing GradCam-generated saliency maps with either using a thresholding or IronNet approach. GradCam is a method that you use to generate the saliency maps that we talked about earlier, and I'll go into more detail about that method in a bit. And then the second step is the semantic segmentation model is trained on the generated pseudo labels and the pixel level expert annotations. And we find that a ratio of expert annotations to the pseudo labels is the best ratio is about 0.9, but we'll get into those results in a bit. So briefly discussing GradCam, which is the method that we used to create our saliency maps. So GradCam was first introduced as a method for natural images in order to improve the interpretability of these CNNs or models. So we have here a picture of a dog, and this is an example used from the authors of the original paper to try to explain why it is that the model classified this image as including a dog. So what you use is you go and find the final convolution feature maps. So in this case, there are 512 final convolution feature maps. And the reason why you use the maps at this particular layer is that the deeper layers in the CNN capture higher level visual constructs. And then you don't want to go any further than that because the convolutional layers will naturally retain spatial information, which would be lost in a fully connected layer, for example. So from here, you also weight these feature maps using the values of alpha. So alphas basically weight the importance of each feature map for a particular decision of interest. So just looking at the formula really quickly on the left-hand side middle here, we see that the gradient of the score for class C with respect to the feature map activations at every region is what makes up this alpha score. And then the gradients are pooled over the width and height of the activation map in order to obtain the weights. Looking kind of intuitively at this, basically what you're doing is you have all these feature maps which have highlighted points of interest, and you want to figure out how much each feature map and each neuron at each feature map contributed to the prediction of the dog in this case. So what you do is you take a weighted average of each of the different feature maps, and then you kind of overlay them together in order to get this final saliency map showing which parts of the image were most helpful for that prediction. And then lastly, what you do is once you have the weighted combination of the forward activation maps, you follow it by a ReLU in order to get your final output. So from here, GradCam can be very easily transferred to the modality of chest x-rays, or basically you follow the exact same setup. This time only you have a chest x-ray image and you're using some trained CNN on those that was trained on those x-ray images. In this case, we used the CNN that we used was a DenseNet 121, and we trained it on the CheXseg train set in order to get our GradCam outputs.
That's great. Mark, can we pause a little bit? You know, in a webinar, it's not always possible to get all the tricky details in, but from the last 2 minutes, what you have presented, if we can take home this lesson that if you have labels and you have the original image, then you can use GradCam to create a saliency map. Is that a good summary? And people can go and figure out what GradCam is. But if you want saliency maps on which part of the image is the network looking at to make a decision, that saliency map, and you can use GradCam to recover that saliency map. Is that a good summary?
Yep, exactly. Okay. Yeah, we're trying to figure out which parts of the images most highly used for getting our predicted output labels. And then we want to use these to train some segmentation model. So yeah, we're going to use GradCam for that.
Got it. Okay.
Right, thank you. And then just talking briefly about what we do with these saliency labels. So the segmentation model that we train is going to need 0 and 1s for every pixel, indicating whether or not that pixel is indicative of the pathology. So we need to go from this saliency map to a segmentation map. And basically the way that you can do this is you can just have a probability threshold be determined per pathology. In this case, we maximize the MIOU on the CheXseg train set. But yeah, basically you just use some thresholding scheme to go from your saliency maps to these segmentations that you can use for training. And then another method that you could use in order to get these segmentation maps is a method called IronNet. So I won't go into great detail here, but basically what the IronNet does is it takes these generated GradCam outputs and it tries to improve the seeds of these by training 2 output branches, a displacement vector field and a class boundary map. So you can read the paper below here if you want more information, but yeah, basically we're trying to improve the outputs of the GradCam method by training a more complex method. And then that leads us to the segmentation model that we're trying to train here. So in this case, we're using DeepLab v3 Plus as the core segmentation model. And this has an encoder part and a decoder part of the model. Basically, the encoder will take the chest X-ray image and move it into some latent space. And then the decoder will take that latent space output and then reconstruct a per pixel annotation of whether or not each pixel is corresponding to a pathology or not. And for our encoder here, we're using a standard ResNet 18 setup, and we're going to use various encoder initializations as well. So either CheXseg, MoCo CXR, ImageNet, or random. And this connects to the talk that Pranav gave earlier about transfer learning. So in this case, we're using a encoder initialization in order to have an encoder that hopefully knows something about chest X-ray image and is able to encode them well into a latent space. So like CheXseg, for example, is a supervised setup where we just train a ResNet 18 model using the standard procedure of fully supervised learning, where we have the X-ray as input and then the pathology scores as output. But in other setups such as MoCo CXR, this is a self-supervised contrastive learning setup, very similar to what Pranav was talking about, where what you have is you want to maximize the agreement between the positive image pairs. So not using your pathology labels at all. And in this case, we're using different augmentations of images from the same patient in order to do that. And then lastly, we also use ImageNet as another form of hopefully transfer learning. And then this is training natural images on training the ResNet 18 model on natural images and hoping to learn some sort of knowledge that we can then apply to this task of chest X-ray segmentation.
Mark, I have a question about, so, you can get ImageNet pre-trained weights for pretty much anything, pretty much any model architecture. What about CheXseg pre-trained weights? Are there standard models trained on CheXseg that people can use out of the box? And do you know by any chance where to find these models?
Yes, so so the training process for CheXseg is pretty easy and mainstream. I would look at the GitHub repo for the CheXseg project.
Okay.
And hopefully, yeah, that should have, if it doesn't have pre-trained weights already, it should have a detailed process of exactly how to reach training in order to get those weights.
Got it. Thanks.
Yes, I think also with this project that we have, we provide some weights that you can use to initialize the encoder as well.
Okay, that's
so
great.
that should be on our repo.
one other question, DeepLab V3 Plus, that's your core segmentation model. Have you tried some newer ones like U2Net by any chance? Or this is the workhorse? I mean, we use DeepLab V3 Plus as well for many of our existing work, but we are also exploring U2Net. By any chance, do you have any thoughts on that?
Yeah, so the way that we selected this model was basically we just ran an ensemble of different models and then found which one worked the best. So in this case for us, it was DeepLab V3 Plus. We were experimenting with UNet variations, but we just found that it wasn't performing quite as well as the DeepLab V3 setup.
Okay, thanks.
So continuing on, so some other methods for comparison that we used. So another method was a fully supervised setup. So this is just training solely using the radiologist annotated images. And another setup we did was the weakly supervised setup, which is solely using those pseudo labels that are turned into segmentation maps as the input for training. So no sort of combination between the two. All right, so this is the overall workflow of our research where we have a chest X-ray input here, and we can pass that chest X-ray through a pre-trained deep neural network and then run GradCam on that output in order to get a saliency map, which we can then use either thresholding or IronNet to reach our weak pseudo label. And then we can combine that with expert annotations provided by radiologists for our semi-supervised method, weighting them with a probability of P. And then if we just use the weak pseudo labels, this is our weakly supervised setup. And if we just use expert annotations, this is our fully supervised setup. Great, so this is some results of combining weak and full supervision, where the value of P determines the expected fraction of images with expert annotations in a single batch. So weighting how much you use expert annotations versus those weak pseudo labels. And we find that there is an inverted U-shape in performance with this variation of P. And specifically, we find that the p-value of 0.9 is able to best take advantage of the more accurate information encoded within the pixel level labels while still utilizing the scale of the weak pseudo labels. And so on the graph here, we have the average of all the different pathologies on the left, and then some per pathology results shown to the right of that. And the pink is the GradCam thresholded weakly supervised, or the GradCam thresholded method for the weak pseudo labels, and an IronNet is in green for the weakly supervised pseudo labels. So that is the result for different combinations of the two methods.
Can I ask you a question if you go back to the previous slide? So it says that 90%, 0.9 is the fraction of expert annotation. So 90% of the images in a single batch, training batch, should be expert annotations, right? But that doesn't preclude us from using a very large set. And from that, we sample, let's say you're using a batch size of 100, then 90% of them should be expert annotation, but this 10, we could sample from a much larger data set. Is that correct?
Yes, that's correct.
Okay.
Yeah, in this case, the weak pseudo labels, even though we're only using them for training 10% of the time, we can use however many we want to input into that 10%.
Got it. We are actually, we need to take a pause and have the questions out, and then we will continue with the rest of the presentation.
Sounds good.
Okay.
Yes, indeed. So it is time for our trivia contest here. If this is your first time joining us, a little reminder, this is open to folks in the Zoom chat due to latency issues. So if you're elsewhere, don't bother answering because you can't win on this one just yet. But the way it's going to work is I'm going to ask a trivia question based on information that was presented in the slides earlier in the webinar. The very first person that answers that question correctly in the Zoom chat window will win a free version of OpenCV, the new OpenCV course, Deep Learning with TensorFlow and Keras, when it is released. So get ready to answer. And if you have won recently, please do not answer. Give other people a chance to win. Let's say the last 2 months. In 2019, the CheXseg dataset and competition launched with over 200,000 X-rays and a leaderboard showing the best improvements with the dataset. Pranav also mentioned 2 other medical datasets that likewise had leaderboards and a competition. Name both of them. Looks like I see Dimi. Dimi is correct. This is Mura and MRNet were the 2 that we were looking for there. Congratulations. Please send 1 email to phil@opencv.org and we'll make sure that you get hooked up with your free course.
And just a reminder that our Kickstarter campaign is ongoing right now. We have about 400 backers right now. And if you want to get this course, it is opencv.org/Kickstarter is the link that you can go directly to the Kickstarter campaign. Even if you don't back us or you have already backed us, in that case, please help us spread the word. Tell your friends and colleagues about it. It helps us support the OpenCV library. So let's go on with this very interesting presentation. I'm all hooked.
Great. Yes, I will share screen again. All right. And one interesting thing or important thing to note about this last slide before I move on is the p-value of 0.9 might not always be the right ratio for your work, depending on the domain that you're in and the availability of the different label types. So this is definitely recommended to be tuned as a hyperparameter for other works that do some sort of similar work between 2 sources of input.
Mm-hmm.
So next, we're going to look at what happens when you, or for comparing the different encoder initializations for our segmentation model. And we find on the left-hand side, we're looking at a fully supervised setup and different encoder initializations. And we find that if you encode it with CheXseg, meaning you encode it using a full or a supervised setup for classification, this is going to result in the best performance. And if you use the self-supervised contrastive learning setup, we find that it's the second best performing, followed by ImageNet, where we're still able to learn some knowledge from, or still able to use transfer learning to learn some knowledge, but it's not going to be as much as using an in-domain data set for pre-training. And then lastly is the random encoder initialization. And then on the right here, we see a similar result where CheXseg encoder initializations are performing better than the other forms, with MoCo, CXR, and ImageNet about the same, and random performing the worst. And in terms of using GradCam thresholds versus IronNet, we see that for the CheXseg encoder initialization, IronNet works better, but if we're using the ImageNet, MoCo, CXR, or random setups, then CAM is actually going to result in an improved performance. I will just quickly move on to a comparison to radiologists. So we find that CheXseg is actually able to outperform our human benchmark on atelectasis, airspace opacity, and pleural effusion. And then compared to the best weakly supervised method, CheXseg reduces the overall performance gap with radiologists by 57.2%. So although on average, it's still definitely performing worse than humans, we're starting to close that gap and reach a segmentation performance that's starting to near or get closer to nearing radiologist performance. And hopefully sometime soon, it can reach radiologist performance or even beat it, as it has done for the classification test of these pathologies.
So there are about 9 or 10 pathologies?
Yes, in this case, we're using 10.
10. Out of those, it's outperforming in 3.
Yeah.
Yeah, it's
So
getting
still
there, getting there.
Yeah, and definitely a limitation with this work is just the limited availability of expert labels that we're using to train on. So we see that some of these really low performing ones are also corresponding to pathologies that we just don't have many labels for, which makes some sense.
Yeah.
And then lastly, here are some qualitative results of our method, comparing it to the ground truth on the left, CheXseg in the middle, and then the weakly supervised setup on the right. And we see that with the, if we look on the airspace opacity results on the right side, we see, even though this is qualitative results, we see that CheXseg is able to get these multiple instances pretty correct on the top left, whereas the weakly supervised method is not getting this right at all. And then on the bottom left, we see with a pretty small pathology, our CheXseg model is able to get this pretty accurately as well, whereas the weakly supervised setup is not. So hopefully we're kind of closing some of those gaps for all the geometric difficulties for the semantic segmentation of these different pathologies. And yeah, thank you for listening. This is our published work with all the authors, and this is the availability of the code and the annotations.
That's great. I have a question for you, not related to this, but in general, working with chest X-ray data. And this is because, you know, one of our engineers was recently working on a blog post on chest X-rays, and he had flipped the image as for augmentation. You know, one of the augmentation was this vertical flip. And I told him we should not do that because the heart makes it asymmetric, right? There's a heart in the middle, right? And that's not symmetrically done. And his response was that, look, everybody is doing it. And he showed me several online code where people are flipping it vertically. And I still asked him not to flip it because it doesn't produce a valid, that augmentation doesn't produce a valid image. What are your thoughts on that? Do you
My
guys?
Midwestern mother would have asked, if all your friends jumped off a cliff, would you do it too?
Right.
Yeah, that's really interesting. So personally, I haven't worked too much with the different augmentation methods that could be used for like really important for creating these self-supervised models for getting that data. But yeah, I think so with the chest X-rays, you could use multiple different views of the same patient. So like you could have one that's the frontal view and then one that's from behind. And I would think like intuitively that should be a better sort of two pairs that have better like actual natural similarity that you can use for this maximization of the similarities compared to just like a flip that kind of destroys some of that actual naturality of what the augmentation could be. So I would recommend, I haven't particularly myself done this task, but I would recommend if there are multiple views to just use those instead of trying to flip it itself. But if it's working, my guess is it's probably like the features that are of importance could be exhibited in that that flipped form naturally. So
right. My concern was that, look, the heart is filled with blood, right? So the heart actually shows up much more solid in the X-ray, and it is not symmetric. And if you flip it, then you may, you know, some water clogging on the lung can be confused with that, and it's destroying information in that area. But yeah, thanks for letting. We are ready for other audience questions also.
Yeah, definitely. We've got a whole bunch of them here. People have been super active on the question forum today. Let's see here. Niraj would like to know, this is one that I'm interested in as well, is you talked about this a little bit, and I think Satya brought up a pretty good example here where it's a little bit different. What are some of the differences and challenges that are unique to medical image segmentation versus, say, more broadly applicable image segmentation methods?
Yeah, so I think in this case, it can be a lot harder to segment certain areas, particularly where if you have like a natural image of, I think the IronNet example was like 2 buses against the blue sky. That should be like pretty easy for a model to be able to segment. These are these huge, very differently looking buses than like the blue sky. So these methods should pretty easily be able to pick up the different like bounding boxes or the bounding areas and be able to segment based on that. Versus like for chest X-ray images, a lot of time it's a bit more unclear. So you could have like extra fluid in a space, but like being able to see that extra fluid is going to be a lot more difficult. Whereas like we pay radiologists a lot of money in order to be able to make those critical decisions, and they have to be able to use these tools to make the decisions versus like if we were to ask you to, or you or me to classify these buses, we would have a lot easier time.
Okay, yeah, that makes sense. And there's, obviously, as we discussed a little bit more earlier, that it's such a, with medicine of any type, it's, there's an increased pressure and an increased level, necessary need for accuracy, because it's affecting people's lives and not just whether or not the computer thinks a dog is in the shot or not, which is a lot of the, the regular generalized use cases here. So it's really interesting to me. Another question here was brought up by Munesh, who would like to know, does any of this, are you aware of any work that uses multiple X-rays of the same person over time to for preventative medicine instead of just things that have become pathological?
Yeah, so I'm not too familiar with that many studies. I think sometimes you can use multiple instances from like different time points of the same patient in order to use that for like pairs of similarity for self-supervised methods. I think there was a paper out of the lab called MEDOG, which may have done something quite similar to that. I don't know if it was over different time points, but they were using the same patients in many different ways to determine how you can best use these the same patient data in order to create pairs for self-supervised approaches. But there definitely should be more information on that.
Yeah, I think there's a lot of opportunity. Obviously, I think it makes sense to almost start at the end where things are more obvious, right? But I think there's a huge potential here for preventative medicine over time that it could be completely, could completely change the game. Amit would like to know a little bit about your hardware setup. What kind of GPUs are being used to train and augment and pre-train and whatnot?
Yeah, so we're not using anything like crazy for this work because we're working with limited data. We don't need anything too super powerful, but I believe we use 1070s in order to train the models, either for the classification or for the segmentation model was just using, NVIDIA 1070s.
Okay, yeah, definitely not. I mean, they're certainly not cheap these days, but not necessarily industrial grade hardware there. It's cool.
They're not 390s.
Right. Bob would like to know, does your system do any normalization of the X-rays in order to get past things like the physical size of the person being X-rayed or the different focal length of the camera or even different FOV of a camera?
Yeah, so there is some normalization that we do where all images are put into the same size. I think it's 320 by 320 in order to be fed into the segmentation model. And we also normalize for the zero mean and one standard variance, but we aren't using normalization of like different camera angles. So there is going to definitely be some some like noisy data there with different views, but it could be possible that maybe using those different angles is also able to help us learn more information about sort of what you can capture with different views. But we're not using any normalization from that aspect.
Word. I think we got time for probably one more here, and we can call her a day. Amit would also like to know, to overcome the constraint of a really small data set, and we covered this briefly earlier talking about the image flipping. Are you using any data augmentation here to sort of flesh out, as it were, the data, or do you think that that is probably not the best thing for this specific use case?
Yeah, so in this case, we actually aren't using any data augmentation, but I think it would be really interesting to look at a data augmentation setup, particularly for those expert annotations that we're using to train, where we have such a limited sample that hopefully you could be able to like just squeeze in some extra knowledge that you're able to gather if you do some augmentations based off of that data.
And likewise, what about synthetic data for this sort of implementation?
Yeah, so I don't know of any synthetic data for the expert annotations, but that could also be really interesting to look at. It may be difficult with the very small sample size you have in order to train a model for that, but that could be very interesting.
So
Could be a really interesting opportunity out there for somebody. Yeah, go ahead, Steve.
I have two thoughts on this, and this is from some experience. Augmentation, we have to be very careful about augmentation here. You can do slight rotation, etc., on the chest X-ray, but be very careful about any kind of photometric augmentation, which means that changing the pixel values, etc., because we don't have, most of the engineers working on these problems may not have enough knowledge about the data, right? And you can easily mess up the data set. You can easily introduce bad things to the data by augmenting it if you don't know what you're doing. With visual data, it's easy. We are all humans. We all consume visual data, right? If you do something bad, you will immediately recognize that, oh, this is not right. But with X-rays, this is not something that you look at daily. And you just introduce some augmentation strategy, you get more data, but is it even real? Is it realistic? Or is it messing up some other things? So you have to be very careful about augmentation. Same thing with synthetic data, right? Be very careful when using any of these strategies, especially with medical data. It's not something that you see every day. And so it is very easy to introduce something bad by your augmentation strategy.
Yeah, anything to add to that, Mark?
No, I think that, yeah, that was very helpful. And there definitely are papers on what augmentations are valid for this modality and which ones you should try to avoid. So looking at that would also be very useful.
Yeah, thanks everybody. Be excellent to each other.
Bye.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by OpenCV Courses. Learn computer vision and AI from the best at opencv.org/courses. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.